All right, welcome. Today, we are going way beyond the basics of subqueries. We're going to talk about how to architect SQL that's not just fast, but truly bulletproof. We'll dig into some really dangerous hidden traps and explore the modern tools that'll help you build your queries, not just, write them. Let's dive in. But let me start with a question for you. What if I told you that a query you've written, one that looks perfectly fine, runs without any errors, is silently destroying or hiding your data? Well, the answer, surprisingly, is yes, that can totally happen, and we're about to find out exactly how. Okay, so let's get on the same page real quick. What is a subquery? Simply put, it's just a select statement that you nest inside another one. You might hear it called an inner query or a nested query. It's a basic building block, right? The result of one query feeds into another. Seems simple enough.
So let's look at a really straightforward example. This is probably the kind of subquery that most of us write all the time. Nothing scary here.
Here's the goal. We just want a list of all the customers who've placed an order. So the inner query runs first, just one time, and it creates this simple list of customer IDs. Then the outer query takes over and just checks which of our customers are on that list. This is what we call a non-correlated subquery. It's clean, it's efficient, and it works exactly like you'd think it would.
But what happens when we flip the logic? What if we want to find customers who have not placed an order? Well, this is where things get really interesting and where we uncover one of the most dangerous little traps in all of T SQL. Let's walk right into the not in trap.
So the task seems easy, right? Find customers who have not placed an order. The most intuitive way to write this is probably using not in. And if you look at our data, you can see there's one customer, Gamma Inc., who fits the bill. So what do you expect this query to return? Logically, you'd expect to see one single row, Gamma Inc. It's the only customer that doesn't show up in our orders table with the real ID. That's the correct answer. But when you actually run the query, you get nothing. 0 rows. The query silently fails. It gives you a completely wrong answer without so much as a warning. So what on earth just happened? The culprit behind this madness is something called three-valued logic. See, SQL doesn't just work with true and false. It has this third kind of weird state called unknown. And this is exactly where the not in operator just completely falls on its face. Let's break down how this goes wrong step by step. First, that subquery we wrote, its list of customer IDs includes a null. That null is a poison pill. Now, the not in check effectively becomes a long chain of and statements. For our customer, Gamma Inc., the database is checking, is its ID not equal to the first ID and not equal to the second? And, is its customer ID not equal to null? In SQL, you can't compare something to null and get a true or false. The result is always unknown. And because just one part of that long and chain is unknown, the entire condition can't be confirmed as true. So the row gets thrown out. That one single null poisons the entire result. So what's the fix? Well, when you're trying to find things that don't match, what's called an anti-join, you should just avoid not in, period. Unless you are absolutely 100% sure that subquery will never have a null. The safe, robust, professional way to do this is with not exists. It's built for exactly this scenario, and it handles nulls perfectly every time. Okay, so getting the right answer is one thing, but we also have to get it fast. Beyond just correctness, we have to talk about performance. And there's a certain kind of subquery that can absolutely cripple your database. We call it the correlated subquery. Now, unlike that first simple example we saw, a correlated subquery is not self-contained. It actually references a column from the outer query. And that means it can't just run once. As the source material says, it has to rerun for every single row of the outer query. So just think about that. If your outer table has 1,000,000 rows, that little subquery is going to run 1,000,000 times. It's a performance nightmare. Putting one of these correlated subqueries in your select list is a huge performance anti-pattern. It forces this slow, one row at a time processing. Instead, modern SQL gives us way better tools. You should always prefer using window functions with the over clause, or maybe a join to a derived table that's already done the aggregation. Both of those are set-based, and they are worlds more efficient. And speaking of modern tools, let's talk about one of the most powerful operators in the T SQL toolkit. It's designed to solve exactly these kinds of complex for-each-row type problems in a really elegant way. So, how would you tackle a classic and, frankly, tricky problem like this? Find the top 3 orders for each customer. or find the highest paid employee in each department. This is the famous top N per group challenge. And while there are a few ways to do it, there's one tool that was built specifically for this job.
And that tool is the apply operator. You can think of it like a correlated subquery on steroids. It's designed to run an inner query for each row of the outer table, but here's its superpower. It lets you use top and order by inside that inner query. A normal subquery just can't do that.
This makes apply the perfect clean solution for stuff like finding the most recent record for each customer, or getting the top performers from every single group, or just replacing a clunky old correlated subquery. Seriously, when you hear a problem that sounds like for each, your first thought should probably be apply. So let's pull all this together. The real goal here isn't just to write code that works. It's about designing queries that are safe, that are scalable, and that are efficient. It's about starting to think like an architect.
Let's just boil it down to a quick cheat sheet for building better queries. Need to check if something exists? Use exists. It's just safer than in. Need to find what doesn't exist? Use not exists so you don't fall into that nasty null trap. Solving for top N per group? API is your go-to specialized tool. And for any other per row calculation, use a modern window function. Simple as that.
And that brings us to the final question. Really understanding these patterns, these pitfalls, and these powerful tools, that's what separates someone who just codes SQL from someone who actually architects data solutions. It's about choosing the right tool for the job every time, not just the first one that pops into your head. So, which one are you?